right. So now we're moving on to the tools demo. But before I do that, I have some updates. The room number is in my phone. Bear with me for the overflow.
It's 8172.
8172. There are signs in front of the elevator. Also, just go to the 8th floor. Also, you might see some cool QR codes around the room. That's if you want to get on the Wi-Fi. That's how we do it. They're sort of posted here in the back. I can see them. And the agenda is also there. Great. So now we're gonna jump into something a little bit more tangible and constrained. We're going to be looking at some exciting tools. This is our first tool demo of the day. This panel showcases novel approaches that at least partially automate the work of aggregating evidence, a Herculean task as the body of rigorous impact evidence grows and no single actor has the right incentives to harmonize this information to multiply its value. SIGA itself is very invested in this effort. We are working with the World Bank, among other stakeholders, to create the Impact Data and Evidence Aggregation Library, IDEAL. This platform will harmonize impact data from RCTs organized by sector. And in the future, we hope to include increasingly common cost data and entirely automate the process of updating this library to make it as useful as possible for decision makers. I'm excited to hear from this set of speakers. Please introduce yourselves at the start of your demo, and I believe we're starting off with Karim, who already got a shout out from Ariana. Who is in charge of helping us? Thank you.
Hello, everyone. Maybe I can take this opportunity to introduce myself. I'm Karim Lasri. I work at DIME at the World Bank, and I have joined the efforts 2 years ago. And today I'm going to be introducing Impact AI, which is the tool that Ariana mentioned earlier today, and in which we aim at making actionable knowledge about impact evaluation studies accessible to you using generative AI.
Yeah, let's. This wasn't here when we tested, of course. Yeah, okay. That's collaborative work here, trying to figure out how to use a computer.
Otherwise, I can use it. Okay. So you're a policy analyst, a researcher, or a policy maker, and you often find yourself asking this type of question. What is the impact of business training on firms? Usually in a situation like this, you would go to your favorite search engine or your favorite aggregator of the impact evaluation literature, search for this question, look for the 100 of results, filter out the relevant papers in the literature addressing your question. Then you would read the papers, try to find the numbers that interest you, which is a very time-consuming process. And life is too short to be that snail. On the other hand, computers think fast, and it is a great time for generative AI to augment humans. If you look at this generative artwork, it won prizes, and it has been generated in seconds, when it would take me 5 minutes to draw a picture of a cat which would look like this. So AI thinks fast, but it is not reliable when answering questions. For instance, if you ask ChatGPT about a very simple question, what weighs more, 2 pounds of feather or a pound of bricks, it will tell you, of course, I know this classic riddle, they weigh the same, when in fact you have 1 pound on the one hand and 2 pounds on the other. So AI is not reliable on questions involving reasoning, and it is not reliable when you ask it questions. So if you ask it the question that we've been seeing earlier, can you show me studies about the impact of business training on firms, it would actually make up some references that do not exist, because generative AI systems at the moment do not know how to distinguish things that they made up from actual facts, like children and some adults. A phenomenon that is called hallucination that we try to find a solution to in our tool. So our solution is to force a generative AI system to find sourced information in a database of distilled causal knowledge before it actually gives insights from the impact evaluation literature. So our tool, Causal AI, Impact AI, would look like this. You would ask it a question, tell me about the effect of standard business training, and then the tool would give you a sourced answer in which it would synthesize the literature, and then you would also be given a nice list of all the papers from the literature that address this question, along with the effect sizes displayed, exactly what you would find in a systematic review, but we make that work for you. So how does that work? When a user asks a question to our system, then that question is formulated in natural language, exactly what you would do in a chatbot of generative AI. And then we would have first a text-to-SQL system, which would convert that natural language query into a machine-understandable query. And that machine-understandable query, which is an SQL one, would be querying our database of structured knowledge, which contains exactly the information you're looking for. So then our system, Impact AI, would gather that evidence and summarize its responses into a text. Literature shows that blah, blah, blah. So the first component, this text-to-SQL component, we didn't aim for something too complicated, given that the questions are usually going to be quite simple. So we aimed for a retriever, which is going to compare the question against a taxonomy that has been developed for IIIE and that we are refining at the moment. And it's going to extract information about the interventions and outcomes you're asking for. Then it would fill an SQL template. And as you can see on the right, the first trials on this system already yield very nice performance, around 0.96 for this retriever at top 1 recall. Then once we convert your question into a machine understandable question, then you could ask how we actually develop this knowledge database. And this is the core of our added value. In order to do that, we take the papers from the evidence literature. And for each of these papers, we extract core concepts describing the causal intervention and outcome that are described in this paper. So here it's just a simplification of that scheme. But as Xin was mentioning, there is the ideal initiative, which is providing an encoding for causal information found in these papers, which is way, way, way more complex. But this is a simplification. So we get this information for each of those papers and augment the knowledge database. And you could ask, how do we get this evidence literature? Because it is a growing literature, and it is not readily available anywhere. So what we did is that we scraped several sources of papers, including EconLit, RePEc, SSRN, Semantic Scholar, and so on and so forth, which got us to obtain more than 2 million econ papers. And from this database of papers, what we do is that we train an RCT classifier to determine whether yes or no, this paper is an RCT. Then we get our evidence literature, and you can see that the performance of our classifier is satisfactory at the moment and encouraging to continue these efforts. And from this evidence literature, what we do is that we extract this knowledge database for each of these papers. So you could ask, how do you read these papers automatically and extract all this very precise information? Could we ask ChatGPT? Answer is no. And the reasons behind that is that there are two main issues. The first one is that the task is hard. You can remember that we talked about this ideal encoding scheme, which is pretty complex, and even for humans, there are disagreements regarding what fields need to be filled with certain text. And this is due to sometimes very complex design or ambiguity of certain fields in the literature. Also, the task is computationally expensive. You know that systems like ChatGPT, they have a limitation on the number of requests. Now imagine trying to feed ChatGPT with 2 million papers, each consisting of more than 12 or dozens of pages. And that would be extremely computationally expensive. And remember that we don't want to be that snail. So our solution is to simplify the task and to leverage smaller models whenever possible. So remember that we got the evidence database and we got the RCTs. And then what we do is we annotate these papers. So instead of just asking a readily available solution to extract that information, what we do is that we're going to instruct smaller models with annotations that are produced both by humans and by an LLM few-shot responses. By combining these two strategies, not only we are able to instruct models, but also we reduce the efforts provided by humans by also relying on these large language models. So from the papers database, we performed an in-domain pre-training on an eConverta. It's a model that we developed in the team that is readily available on Hugging Face. This model, by having been pre-trained on the literature, it is knowledgeable about the literature. Then we supervise it on our annotations produced by humans and by our LLM in a few-shot setting. And the results are that if you compare ChatGPT without instruction to our model, we double the performance. And that's only with few annotations. So the limiting factor here is to obtain more data that has been annotated to keep supervising smaller models. Not only the advantage is to increase performance by having a specialized model, but also we reduce the computational cost by having a smaller model. Then remember that the second strategy to tackle this issue of extracting information is to slice the complex task of having one whole paper and getting all the information from that paper using one single algorithm into simpler subtasks. So we have our papers from the literature. What we do is that we are developing a parsing algorithm, which is going to take each of these papers and extract the table of content, which is not given in most papers, in a structured hierarchical way. Not only with this, we are able to slice the full text of the original articles, but we are also able to give it meaning with the nested structure of titles in order to look for the information we're interested in for each of the concepts at the right place of the paper. So this alleviates the modeling tasks quite a lot. The second strategy is to extract the tables. So instead of giving the full PDF paper to an algorithm and to just asking to find the information, we know that the figures are going to be found in the tables. So we have developed our own module for extracting the tables. And from both of these, the outcome of both of these, so that is paragraphs, structured, and the tables, what we do is we take all of the concepts we're interested in. So this includes intervention, outcome, effect size, and so on and so forth. We score them for their likelihood to be present in each of the sections or the tables. And then what we do is we simply extract them. And by slicing the task like this, we are not only reducing the computational cost, but also increasing performance because simpler tasks are easier to solve even for the complex generative AI that we have today. So the limiting factor here, even by slicing, is annotations. Because recall that we've seen that few-shot and even zero-shot models that you try to query without further instructions, they don't perform well. So even if we slice the task like this, the limiting factor really is annotation. And this is a key message also for any automation task. So the expected outcomes from this project, the first one is that Impact AI, our tool, will radically scale up the use of causal evidence. That's what we believe. And it will support the achievement of the United Nations Sustainable Development Goals. Also, the second outcome is that we're providing a lot of public goods for development in the development AI area by providing an open source economic specific LLM, but also a queryable impact evaluation database and datasets of impact evaluation papers that have been annotated either by humans or by models, but with very controlled and targeted information for causal knowledge. So I would like to thank our magnificent team that has contributed these efforts, including all the robots. And thank you very much for listening. Please scan this QR code to keep posted on this. Thank you.
All right, thank you so much. Very exciting work. We're moving right along. We're already behind schedule. Sign of a good conference. It's my pleasure to introduce Jahnavi from ID Insight, who'll be telling us about Ask a Metric. Thank you so much. She has the distinct honor of probably being the presenter that traveled the furthest to be here. So we're very appreciative of your efforts.
Thank you, Sean. Hey everybody, I am Janvi Meher and I'm a product manager from ID Insight. ID Insight is a global advisory, data analytics, and research organization. So today I will be presenting a tool that we are building that is called Askometric. It is an LLM powered tool and we are hoping to reduce the barriers to data usage and hopefully democratize data analytics. So how do decision makers access critical data? Let us look at an example of a decision maker who was an official in the healthcare department of the Tamil Nadu state in India. This official has this key question which they're looking to answer. Which district in Tamil Nadu has the highest number of beds in hospitals and clinics set aside for COVID patients? Typically, based on our experience in working with non-profits and governments, we have observed that decision makers interact with dashboards in order to get this data. They usually use their mobile phones and look for indicators on the dashboard. In this case, the indicator that they're looking for is the number of beds. There exist several challenges with dashboards. Dashboards usually present the highest priority cuts of data and do not have a comprehensive statistics of the underlying data sets. So the indicator that the decision maker is looking for might or might not be present on the dashboard. This presents them with further challenges and they'll have to engage and interact with the dashboard further in order to dig out this data. So they try to apply filters, slice and dice the data, try to run some SQL queries. Often we have observed that the decision makers do not have the technical capabilities also to interact and engage deeply with the dashboards. So they end up reaching out to data analysts or data administrators to get this information. As you can see, there exist many challenges in order to access data, and this puts up a lot of barriers in order to use data to facilitate decision-making processes in a timely manner. To solve for this, we are building a tool called Askometric. So again, let's look at the example of this decision maker. So here, the decision maker simply has to open a messaging service, which is typically WhatsApp in the Indian context. They input their query using a natural language. They can use English or they can even use language according to their local context. In this case, that would be the Tamil language. The question then gets passed to the Askometric Fast API endpoint, which invokes the LLM agent at the backend. Here we run a series of checks. We have built-in guardrails to ensure that the question that the user is asking can be responded to based on the data that we have in the underlying data set. Once these checks are successfully passed, we construct an SQL query, query the database, and return the response back in the natural language to the users. This is sent back on WhatsApp, and it's in the same language that the user has used to input the query. This reduces the time it takes to access a particular indicator and makes the data readily available to the decision makers. So let's take a quick look at a demo for Askometric. So we are using a publicly available data set. So this is the COVID data from the Tamil Nadu state in India. This demo has been set up using a WhatsApp interface. So you can see that the first question that we are asking is how many beds with oxygen supply are available in total in Perambalur. So Perambalur is the name of a district in Tamil Nadu. So you can see that the response has been generated. We are also displaying the SQL query that has been constructed by the LLM. We use this to quickly back check the data and look for the accuracy of the performance of the LLM. So in the next question, we are inputting the question in the Tamil language. So here we are asking how many beds are empty in the Kadalur district. So we are waiting for the LLM to respond. Yeah. So again, there is a response that is generated. There are 868 beds that are empty, and this is in the language which the question was inputted in. So let's try another question. So here, like I mentioned, the underlying data set that we are using is the Tamil Nadu COVID data set. So we want to check if the LLM will hallucinate or not. How many COVID cases are there in the USA? So here we have built-in guardrails to ensure that the response is only related to the data that is present in the data set that we are connected with. So we do not get a response for this case, and the tool says that, hey, you cannot access this data because this information is not present in the knowledge base. So we are back to the question that we started with, which the decision maker had. Which district has the highest number of beds in hospitals and clinics set aside for COVID patients? Cool. So just moving on to the journey of building Askometric. So we started building in Jan 2024. It's been 4 months now, and we have a minimum viable product in place. We are currently piloting this tool with a non-profit organization in India. I wanted to take a minute to highlight the top 3 learnings that we've had in this journey so far. So having clearly signposted data improves the performance of the LLM by quite a bit. Having metadata, a code book, columns and tables that are well labeled helps in improving the performance of the LLM quite a bit. In case we have underlying data that does not have metadata, the columns are vaguely named, the tables are not clearly named, then it becomes difficult to predict the performance of the LLM. The responses can vary quite a bit. So a lot of the time that we spent in building out this tool also went into data cleaning and setting up the data sets which the tool can use in order to produce accurate results. Setting up validation data also requires contextual knowledge. So by validation data, we mean the question answer pairs that can go as an input into the model. So here the question would be the natural language query which the users would probably want to ask, and the response would be the SQL query generated by the LLM. Having an understanding of the users, the types of questions that they seek to answer using the data helps in setting up validation data that is more useful for training the LLM. As with any LLM products, extensive testing and monitoring is required in order to ensure that the performance is reliable and accurate. On the roadmap for us next is cost optimization. Currently, we are using GPT 3.5 and GPT 4.0. We want to experiment with other open source LLMs in order to benchmark their performance against these models. We are also working on improving accuracy and explainability using RAG, schema pruning, and more complex agentic workflows. We are also wanting to make the application management more self-service, especially to a less technical audience. We are also working on refining the onboarding process for new organizations. So get in touch with us if you're interested in learning more about how we went about building Askometric. We would love to give you access to a demo setup. We also want to collaborate with other organizations who are working in the space. We want to test out the tool in multiple contexts, get learnings, and refine it further. I would like to close by introducing the team at ID Insight, which has been responsible for building, testing, and deploying Askometric. Thank you, everyone.
All right, now we have Ivan Solario from the World Bank. Please.
Thank you, Solatorio.
Sorry for this.
No, it's fine. Thanks. Oh, okay. So, hi everyone. I'm Ivan Solatorio. I'm a data scientist working at the Office of the Chief Statistician at the World Bank under the Data Development Data Group. Yes, thank you very much.
It's in PDF.
Yeah, it's in PDF. Sorry. That works, right? Yeah, I think that works. Oh, there you go. Okay, perfect. Thanks. So, I think for me, I'd like to present our work, a compendium of like activities around AI for data, where we kind of think about how in the age of generative AI, we can actually make use of these technologies to improve data. Oftentimes, we think about AI as a means to use data to be fed into these AI models to get outcomes, but we kind of like want to change the way we view data. We want to see it as if it's something that benefits from these technologies. So let me walk you through some of this. So the motivation behind this activity is that, well, we know that data is abundant, but finding relevant data is very difficult. And we see two things that basically cause this. Basically, data doesn't really come with rich metadata. And even with all the technologies available out there, some data systems, or most data systems, still do not integrate the relevant technologies. And so we want to rethink the potential solutions to these problems. And this is a brief overview of the topics that I will be talking about. So we will be discussing our work on data discoverability, how we view AI for metadata augmentation, and how it can be useful for data dissemination. Okay, so finding data with AI is basically, currently semantic search has been a very mainstream term, but like a couple of years back, before ChatGPT, it's still a bit an alien term. But the idea behind that is we can kind of abstract the way we interact with text. Before, we think about finding information through keywords. However, there are already means for us to think about finding information through its meaning. And that is like how semantic search allows us to do. Basically finding information through its meaning. And what does it mean? So basically, it's just a 4-step process, right? When you have a collection of text, you just find a model that can help you convert this into numerical representations. These representations are some mathematical compression of the text, but hidden behind the model is the representation of the meanings of this information. And now, when you want to find something, it's just a matter of like converting whatever the user asks to the same numerical representation and do some mathematics using very simple trigonometry, geometry, and then that would allow you to come up with very relevant information. And now the question is, how can we use it, and how can we see the difference between semantic search and what it offers compared to the traditional keyword search? And so we kind of like put up this very small demo that would allow you to explore and see how, for example, in this example screenshot I did, if you put teen mortality, it understands that the relevant indicators are those in the age between 15 to 19. It understands the concept of teen. It understands that these are the age range that represents the teen. However, if you just do the keyword search, it gives you, yes, mortality, but not in the relevant context that you, as a who wants to find information, actually cares about. So, how do we make semantic search work? One of the things that I've shown here is that the key ingredient is this embedding model. And one of the things that we're thinking is currently, large companies, just spend millions of dollars to train models to be very powerful. But we are thinking that in the countries that we care about, in the places that we care about, they probably don't have GPUs, right? And so we are thinking about creating a models as public good. In that sense, we train models that's very small, but at the same time, really powerful. What that means is that we have published our embedding models in Hugging Face in the embedding leaderboard, and actually, this is OpenAI's. And basically what we say is that we can compete with large companies. And just within the span of 3 months, these models that we published have already gotten about 600,000 downloads. And I can only imagine the different use cases that these people have used this very small but powerful models for global public good. But at the same time, finding information just through semantic search is not enough. Assuming we have good metadata, we can leverage the structure of how the user finds information to our benefit, to improve the way the information is given to them. For example, here, we use this open name entity recognition model to parse this particular query. By doing that, we can exactly capture relevant geographic information, years, and so by integrating this system into data catalogs, for example, we can precisely tell people that, okay, Philippines, let's take that country from the database, get the year, and actually give the user upfront the value that they're interested in. Now, so all of these data discovery systems won't work if we don't have rich metadata. What that means is that the data only comes as a, sometimes CSV file, Excel file, but what does a header mean? Now, sometimes you have age, sex, V1, V2, and so what does this V2 mean? We don't know. And so that's like, it's essential for any data set to have rich metadata. And corollary to that, we want to augment the available metadata with as much information as possible by using generative models. And so one of the very low-hanging fruit application of generative AI for metadata augmentation is just to generate keywords. That way, any systems that implement keyword search, as is right now, can benefit with this value add. But the second, in the more kind of deeper value is it possible for us to just take all of the header information from a text and come up with themes that these data may actually help inform? For example, if I have a field that contains age, height, weight, and so on, is it possible to know that this data set may be useful for studying malnutrition? Because I can compute, body mass index and things like this. And that is precisely what we did. We came up with a framework that actually allows you to just input this, variable labels or headers, and do some semantic enrichment through NLP to improve the signal-to-noise ratio we can get from the data, and then use the LLM to generate the potential themes, and use an AI agent that would quantify self-consistency to reduce hallucination. And basically, this is an example of what we can get from this system. And it understands French. So basically this represents the label of the fields in the data. And we fed it into the model, and it understands that these variables can inform themes around health and COVID-19 prevention measures, government policy awareness and compliance. And so all of these now can be fed into our semantic search systems that would allow people to find data better. So these are two things of how we view AI can help with data augmentation. But what do you do after you have the data? We want to disseminate data. And also at the same time, after people use data, we want to measure how they use it. So I think the previous presenter showed something similar. And we just want to show as well some of our views around chatting with data. And for us, it totally depends on how your use case is, but we kind of err towards the side of safety, and so we think that we can't just use a text to SQL, but it has to be an API driven interaction with the data system. And now we go to the measuring of data use. So this is a very interesting and actually challenging field, because oftentimes people spend like millions of dollars to produce capture data, put it out in the open, with probably barely minimum, visibility around how many people are using it, how it's used, where it's used, and so on. And so we are thinking of ways to use AI and LLM to actually capture and understand this landscape, be able for us to quantify how the return of investments in data, how people are there gaps in how people find data, and so on. And so basically, we simplified the problem by, okay, if I have a document, if I have a compendium or collection of research papers, can I understand where data set has been mentioned in the context of it being used to inform outcomes in the paper? And so what we do is, it's not efficient to just pass an entire paper, but we want to improve the signal-to-noise ratio, and so we do it in a sentence level. And we don't pull the entire paper out. We just train a model that can tell us, okay, these sentences are likely to contain information that you care about. And then given this top n, potentially likely sentences, we pass it to an LLM and get a structured information out. And so this process, we can scale, and then we can, run it through all the millions of documents out there and come up with a landscape, whether the LSMS or the WDI or the consumption price index has been used in the context of economics, nutrition, health, poverty alleviation, in what year, in which geography, and so on. But at the same time, this is the last slide, sorry. At the same time, it's difficult sometimes to have the relevant information that you want to train a model. And so, for example, in this data use context, right, we also want to understand in which context a data has been used. We have a topic taxonomy at the bank, but the training data is barely available. And so what we see is that with generative AI, we can probably take these topics, ask it to generate example of sentences that probably pertain to these topics, do some Bayesian update to ensure that we have a uniform, availability of data for us, then generate this, so on and so forth. And then once we have sufficient number of data available to us, we can train a small model that just specializes on predicting topics. And so these are ways for us to think how we can leverage this highly invested, powerful LLMs to our benefit and convert and condense all of this information that they have into models that are accessible to people with, who doesn't have GPUs or whatever. And so I end there. But I acknowledge the KCP for funding parts of the work in data use and related activities. And thank you so much for the opportunity for us to participate in this event. Thank you.
Terrific. We're moving right along. It's my great pleasure to bring Dunstan Metakenya to the stage. Thank you so much.
Thank you. Good morning. I think it's still morning. My name is my name is Dunstan Metakenya. So my work is at this point less of a tool, but it's still important experiences that I'm going to share from working on audio data from Malawi. And I think I just want to start with going back to the keynote speaker who emphasized, Dan, he emphasized that in order for AI to work in low-income regions where the bank is mostly working, we need to adapt the AI to work in those regions. And one of the main adaptations in those regions is really data. So I think it's very obvious that most of these models don't work very well for low resource languages. So these are very small languages in countries like Malawi. So I'm going to share my story of how I worked on this particularly difficult data correction for speech, which is even more difficult compared to text. So I'll briefly talk about Malawi, the country, and some of the main languages which are spoken there, and then specifics about this automatic speech recognition project, and some of the current use cases for speech recognition, and finally talk about some of the technical challenges as well as next steps and call for action. So for those who don't know where Malawi is, I mean, for this audience, I suppose you know where the most of the African countries are, but that's where Malawi is. And also to mention that I come from, if you didn't pick that up from my accent, East African accent, I come from there. So the main languages spoken there, the main one is Chichewa. There it's shown as Chewa, but it's also known as Chichewa. So 70% of the population speak the language. Another issue which is shown here on the slide is also literacy rates, which will become obviously important for speech recognition. So it's not super low, but it's still, I think, considerably low, especially for women. So that will become important, as I'll show you later. And again, showing the top languages just to show that most of these languages are not supported by the existing natural language processing, natural language understanding. So that includes, of course, ChatGPT. And obviously, speech processing is like the most, it's the least supported for most of these languages in the country. So obviously, that's why automatic speech recognition has a lot of potential for these countries, just to help in bridging the digital gap, as it's often called, simply because using speech is very easy, as we all know, but also because of the low literacy rates. If a person can interact for example, with a medical app using their speech without having to write if they don't know to. It makes technology adoption very fast. So the details of the project, I have to say this was mostly a labor of love project. It was an extracurricular activity project. But my main goal was essentially to work on data collection, so language data, speech data for most of the local languages in the country, but currently focusing on just the top language, Chichewa. But of course, once we have the data, what I wanted to do was also to try to see how far I can improve the performance of the foundation-based models on the given data. So the second objective here, as you can see, is model fine-tuning and doing a lot of experiments on this language. And then, of course, documentation. Again, for the low resource languages, we don't find a lot of documentation. So just improving documentation on the performance, which models are working better, how to fine-tune the model. So these are the three main goals. Just going into details on these goals, of course, for the data collection. For speech, mostly you can collect speech as unlabeled speech, but also want the speech to be labeled, so transcription. Also for these models, even for speech, we still need a lot of text. So for low resource languages, the main characteristics of low resource is that there is very little data online, right? That's why they don't perform very well. So being able to have a lot of text corpus for the language. Again, model fine-tuning, it sounds very easy, but there are a lot of models there. It's a zoo of models. So if you have a smaller language X, how do you choose the foundation model to use? Which model is working better? How much data do you need to fine-tune? All those type of things. And then, of course, documentation to make sure that others can learn from you, and being able to showcase with apps and demos. So data collection, briefly, it's just text. I was really focused on trying to get data from institutions because I believe that there's a lot of existing data with institutions. If you go to Ministry of Health, they have translated some stuff there, so you can find machine translation data sets. If you go to broadcasting stations, you can find audio data there. So that was one of my kind of motivation to try to find existing data, and also just using very cheap methods for collecting data. I'll show why that didn't work very well. But up to now, the main achievement for the data is the project has around 100 hours of speech. So out of those, it's about 35 to 40 hours is transcribed. And then for just text data for Chichewa, we have around 5,000 news articles. I think if tokenized, it's a couple of 100,000 of tokens. I was also collecting Chichewa local language textbooks, and then for machine translation, around 15,000 sentences. Just some key features about the data collection. I was really focusing on cost efficient, so using WhatsApp as a mode of data collection, right? Instead of getting an app to a specific app for people to install because the project doesn't have so much money, just using WhatsApp. For speech data, you really need to have the data from diverse population across the country as well as age. Again, leveraging existing data sets. So this is an example of using a WhatsApp app. So that sounds mouthful, but using WhatsApp, first I just want to mention that one thing I tried was to harvest existing voice notes. So if you've worked with people from Africa, you know that people share voice notes extensively. So what I did was I said, okay, well, people are sharing voice notes, and when they share voice notes, mostly they're using the local language or vernacular language. So I was just collecting those voice notes. The main challenge there is, of course, obviously the copyright issue once you collect those, but definitely it made it a bit easier. But it's difficult to automate. The data can be noisy because you're just getting everything you're finding on WhatsApp. So instead, I think another approach was to create a specific app for this data collection. So what you see here is that okay, maybe I should finalize this. You see that this specialized app enables the data contributor to either upload an audio in the local language and transcribe, or they can read a sentence. So the sentence was provided. So I just had a bunch of 50,000 sentences, randomly generate that. Someone reads the sentence, so then we get the data. So this provided us with much cleaner data. And again, this is to show the distribution of some of the contributors from around 10 districts across the country. we're able to generate 16 hours of data from reading, which is good because you don't have to transcribe that. And then 6 hours was just uploaded audios without transcription. That's the achievement on the data collection. Model fine-tuning, again, these are the main goals, the obvious ones, just fine-tuning the models, customizing, benchmarking the performance. Again, we have to know for this language which models are performing better, and documenting. I'll not share too many results for this, but the two main models I tried were the Whisper from OpenAI and the Multilingual Massive Speech model from Meta. The performance is very similar, so the two models are very different in terms of the architecture. So the Whisper model is sequence to sequence, while the MMS is a wave to vec model. The surprising thing was that the MMS model was performing usually better, but when you try for the speech, for the actual performance, when you upload a speech for transcription, it was doing pretty bad. So essentially, I'm mostly using the Whisper-based model. You can try and test the transcription, but you have to upload Chichewa. So if you know one sentence in Chichewa, you can try it. Yeah, so this is a speech transcription for Chichewa, so you can still try if you've gone to Malawi. But the main use cases, and one that I wanted to share here is, of course, there's a chatbot for agriculture which is being piloted in Malawi by a company called OI. So they are using this model for speech to be able to allow people to use speech. Another one which is more relevant for here, of course, is processing social research interviews. So there are several interests of people who I'm working with to try to use this for social research interviews. So the main challenges, I have 1 minute. The main one, of course, is the data collection, obviously. As I said, I'm using cheap methods. So this usually, it has led to a lot of noisy data. So down the stream, even fine-tuning the models is difficult to get better performance increase because of the noisy data. The institutions have a lot of local language content, but it's not as easy to get the data from these institutions. Model fine-tuning, again, challenges with GPU and costs. The use case of automatic transcription of interviews, this is what I've just started working on now, and some of the challenges include, of course, most of the models are meant to, at least when you just fine-tune them, they are meant to transcribe very short audio chunks, like 30 seconds. So when you transcribe an interview, which is 1 hour, then the performance decrease pretty substantially. So there are challenges with that. And then, of course, financial resources. The main call to action and next steps is just to document the data that we have now and focus on experimenting with the models and fine-tuning, and then automatic transcription for qualitative research interviews. So that's why I'm making this call. For those who are experts in analyzing like qualitative data, focus group discussions, I'm really making this call, looking for collaborators to work with me on evaluating some of these models. Thank you.